Welcome back, everybody, and welcome to these 2 coming weeks where we're going to spend most of the time on the second midterm, and most of the theory, which we will talk about today, and also on Wednesday, and parts of next Monday, is going to be very much directed towards the second midterm, which I think is the most fun part of this course, actually, writing this code for the solar system. I mean, at least it was for me. And every year when I ask, should we do it or not, there's been a popular vote, yes. Now, so this today, we are going mainly to look at a kind of interpretation of the orbits, which we may have. And when you play around with your Earth-Sun system, you will actually see these possible types of orbits. Then later, we're going to add Jupiter to the Earth-Sun case. And finally, we are going to have a program which simulates the solar system with the known planets. And every year, there's somebody who adds all the moons and everything else you can think of adding to the solar system. Feel free to do that, but try to gauge your time. And unfortunately, we can only give you 4.0 here. So even if you add many fancy things to the projects, we obviously cannot give you more points than those which can be achieved. But feel free to enjoy these things. And so Wednesday, we are going to look at the second midterm, and we are going to repeat things a little bit about Kepler orbit analysis and so on. And then we will use parts of the lecture to study the midterm. And Friday is just the midterm solution. And then we repeat much of the same thing next week as well. But before we move on, I obviously have to make a small confession here. So I promised to have this grading of the first midterm ready by the weekend, but I am a horrible procrastinator. And this weekend, I was basically here, and perhaps I ended up here. And today, I'm here. Okay, so, but I'm going to try to be done with it as soon as possible. I apologize for the delay here, but actually this weekend, I didn't do anything. Okay, guys, sorry for that, but let's move on to the topic this week. And in the lecture notes here, the slides, you will find things which are tightly linked with the midterm, but I'm going to do things on the whiteboard first. I also remind you of where you can find the midterm. So there's under the folder doc midterm projects, second midterm, and then you can find both PDF files if you prefer that, or a Jupyter notebook if you prefer that. And the first part is actually you looking at the Earth-Sun case. And we had that one in that homework after the unlucky and sad week. So which is a homework, which if you do it, you get extra points, but you don't need to do it. Homework number 5. You find the solution to that one. There's the Earth-Sun modeling there. And if you look into the text, don't use the equations in polar coordinates, but you should actually do everything in Cartesian coordinates, because that's going to be the easiest one. So in the beginning, it's just some kind of background, but when you're setting up the code for the Earth-Sun case, you should do that in Cartesian coordinates, because that's the easiest one to do numerically. So if you now go back to the homework from last week, homework 8, where you did the harmonic oscillator in 2 dimensions, the only thing you actually need to do is to take that code and replace the force, which came from a harmonic oscillator potential, with a gravitational force. Essentially, that's the only thing you need to do, in addition to scale some parameters, which we're coming back to on Wednesday. Any questions so far? So I'm going to dive into the whiteboard, and look at the analysis of the type of orbits and link that with the type of energies which you can expect and the type of motion which we will get when we look at the gravitational force problem. So we will mainly stay there, and then we're going back to the codes if we get time. If not, we will do that on Wednesday. So parts of Wednesday, we are going to go through some demonstrations, and then we use the rest of the time to study the midterm. Okay, so let me switch over to the whiteboard here. And I hope you don't mind if we spend, that we link the lectures with the midterm. And also, as we had with the first midterm, please don't hesitate to ask questions. The most important thing is actually the dialogue we have when we are solving this type of problems. Okay, so let me give you a quick reminder of the type of problems which we are going to face. So we have we made a transformation to the central mass frame. So this is a short repetition of what we have done, which means that we put the central mass coordinate equal to 0. So that's a pretty common choice in physics, especially if we're looking at the reactions and scattering between objects. And then we transform to polar coordinates. So that means that we had an r times a cosine phi, and then we had the y, which is given by r times sine of phi. And then we know that the radius lives between 0 and infinity. And the angle phi is now defined to live between 0 and 2 pi. Now, the differential equation which we ended up with then was 1 for the radial motion, which we would write as mu times the radial acceleration, which is given by some kind of external force, plus this centrifugal barrier, which is a term which comes from the kinetic energy. And then we had the other differential equation, which is the angular velocity, which is now given in terms of the angular momentum divided by the reduced mass and r squared. And then we showed in the very beginning that angular momentum is conserved. This is just a quick repetition of what we have. We showed that the linear total momentum is conserved. And these two results, they follow from the fact that we have internal forces only. And this force which we have is something which depends on a function which we haven't specified with the absolute value of the relative distance multiplied with the relative distance between two objects. So these are things which follow from the assumptions we have made about the system, that we have internal forces only, and that the force is proportional to the radius or the relative distance between two objects. With that, then we could show that angular momentum has to be conserved. Okay, and then we knew that the kinetic energy is given by 1/2 times mu, and then we have the radial velocity plus r squared times the angular velocity. And this term, the second term, is a term which we normally bring into an effective potential, but the potential in itself is something which we are going to write in terms of a parameter gamma divided by r to some power of beta. And when we have the gravitational force, beta is equal to 1. And then we defined an effective potential, which is simply this V of r plus this term, which goes like L squared divided by 2 of mu of r squared. Now, the differential equation, the nice thing now is that we could actually solve this differential equation, which we have here, the one for the radial acceleration. This can actually be solved. since angular momentum is conserved. So we could actually find a solution now with the energy conserving forces, angular momentum conserving, linear momentum conserving, in terms of a parameter, c, plus another parameter, epsilon, which is called the eccentricity, times an angle cosine phi. And this parameter c is given in terms of the angular momentum divided by mu, the reduced mass, multiplied with this parameter in front of the potential. And if we have the gravitational force, that contains the gravitational constant and the product of the two masses. And then we have this eccentricity, which is given by A, which is a constant, which we determined from the initial conditions. So this is a constant multiplied with L squared divided by gamma times mu. So this is just a quick repetition of what we've done. And what we found is that if we took epsilon equal to 0, this is the first case, then we found circular motion. This is something we did last Monday. And if we now plot this potential, if we do that, so we get something which runs like this. This is the effective potential, V effective. This is the total energy as a function of this relative distance, and it's only the magnitude of that relative distance. And then we could then find a minimum here, which then corresponds to circular motion. And then we have an R min for circular motion here. And in that specific case, we can find this R min. How to find R min? What we are doing then is simply to calculate the derivative of V effective. So this is the effective potential. And then at R equal to R min. And we want that one to be 0. And just to remind you that for the gravitational force, or just one of these types of forces, this V effective is actually given by this V of R, which is a gamma divided by R times beta plus L squared divided by 2 mu over R cubed. Now, one of the things which you would actually need to do in a project is actually to find this R min for circular motion. So I'm just going to give you 2 to 3 minutes, and we just take the derivatives and find R min. That's okay. So just a small exercise, because this is something we will need in the second midterm. So if you take the derivative of that form as a function of beta, because in the midterm, you're also going to study different values of beta. R to the power of beta. It's my lovely handwriting which kicks in. Okay, let me write down the answer. So if I did it correctly, and you guys can correct me there. So this is going to be given by L squared. So I'm just making it a little bit more general now. Gamma times beta times the reduced mass here. So if you do the standard gravitational force, or that type of interaction, which we get also for a Coulomb type of interaction, then beta is equal to 1. And then we should have an R min is equal to L squared divided by gamma times beta times, no, beta is equal to 1 then, so we don't need to put that one in. So in the exercise, when we are setting up different constants, you probably notice that a very simple way of doing that is to put all these constants equal to 1. And then clearly R min should be equal to 1. So that's a very useful test when you now are developing your codes. So just put all the constants equal to 1. Now, there's something I want you to think of now. So I'm not going to give you the answer, because in the exercise 1, you actually ask to study the motion you get when you put beta equal to 2 and beta equal to 3. And the question then, when you run numerical simulation, is whether you will get a stable orbit or not. So the type of forces you will get are forces which conserve energy and angular momentum due to the specific behavior 1 over r, which you have. And we are only going to deal with internal forces, but you will see that something strange may happen here. And this is part of the analysis which we want you to do in exercise for part 1. It's the last part, is exercise 1D, where you will play around with different types of gravitational forces. So in a certain sense, you could just play around and see what gives you a stable orbit around the sun and what does not give you. So that's a kind of experimentation where you try to figure out whether this type of interactions or forces or gravitational potentials, whether they give a stable orbit or not. And then you can go back to the mathematics, and when you analyze a problem, you can see that for some of these parameters beta, you will not get a stable orbit. So this is something which you have to study in exercise 1. We are coming back to that. So I'm going to highlight this one for beta equal 2 and 3. So part 1 in the midterm asks about stable orbit and not. So this is something we will come back to. So let's just highlight that one. So this is going to be one of the explicit questions. Now, if you now look at the next case which we had, which is also something we ended on Friday, we now looked at this parameter epsilon, and we did not specify why it was less than 1, but we had the case when we looked at this parameter epsilon, and then we could find a new R min. So this is different from the one we had previously, so I'm going to put a prime on top of it, which is equal to C divided 1 plus epsilon. And then we have an R max, which is equal to C of 1 minus epsilon. So it means that when we are looking at the way the orbit is going to look like, the system, so this is the distance between the Earth and the Sun. And in the case of the Earth, this difference between R max and R min is very small. So which means that the aphelion and perihelion are almost the same as the distance between the Earth and the Sun. So that stays almost constant. So the Earth's orbit is going to be almost circular, just a small deviation from a circular orbit. So what you will see then is that this oscillates if you take this as a function of time. So the position which you're going to have will oscillate between R min and R max. And the period, T period, is going to be equal to 2 pi. So when you've gone a period of 2 pi, then you will be back to R max. And if we go back to the figure which we had. This means that we will be here somewhere, and we will show that this corresponds to an energy which is lower than 0. So this is R min prime, and this is our R max prime. And in this case, we are going to have an energy here. We have an energy here. So both these energies are less than 0. This is the prime energy, and this is the one for circular motion. So this is the one which gives us elliptical orbits. And I will just repeat what we got on Friday, so that we have everything in one page. So we defined on Friday, we defined a new constant D, which was given as the C times epsilon of 1 minus epsilon squared. And then we defined another constant. So we just played around a little bit, algebraic manipulations of the equations we have. So we define these constants, B, which is equal to A minus epsilon squared. And what we could find then is that we had a typical equation for an elliptical motion divided by A squared plus a Y squared divided by B squared, and this is equal to 1. And we showed also on Friday that this R max is the same as this constant A plus this constant D. Now, what we need to say something about now is the energy. So till now, we've simply looked at this eccentricity epsilon, but we didn't say anything about the energy. And what I also said is that this epsilon is larger than 0, because when it's 0, then we have circular motion, but it should also be less than 1. And this is linked to the type of energy which we're going to have. So let's make an energy consideration now. So energy consideration. So the energy is now going to contain this term, which is given by the radial velocity, r dot squared. And then I have this effective potential, which contains a term from the kinetic energy. So this is given by 1/2 of mu of r dot plus this V of r, which is simply, which we don't specify yet, plus L squared divided by 2 mu of r squared. Now we're going to make an assumption. We're going to make an assumption that at r min, so it's a little bit like what we did in the first midterm, where we now assume that at this position r min, that means here, we can assume that the radial velocity is equal to 0. So that means that when we now look at the total velocity, there will only be a velocity which comes from the angular momentum. So what we're going to state now at r min, we are going to say that dr dt, which is equal to r dot, is equal to 0. If we do that, then the energy which we get at r equal to r min is now simply going to contain the potential energy. So there will be a minus gamma divided by this r min plus L squared divided by 2 times mu of r squared min here. So that's the total energy of the system. So this is something like when you are going to model the equations of motion, you can assume now that you place yourself initially at r min, and then you give the system a radial velocity, which is 0. And then you can see whether this gives you the right motion which you would expect, whether you get an elliptical type of motion. So that's one way of testing the physics, which we have here. Now, this is something which we can rewrite. So we can rewrite this in terms of 1 divided by 2 r min. So this is just an algebraic manipulation of the equation which we have here. So we have an L squared divided by 2 of mu multiplied with R min and minus 2 times gamma. And now I'm going to plug in R min. So R min is given by C divided 1 plus epsilon, which is nothing but L squared divided by gamma times mu multiplied by 1 plus epsilon. So the next stage is obviously the exciting insertion of R min into that equation. And then we can simplify it. And from that, we will see that if the energy is below 0, then this epsilon cannot be larger or equal to 1. So we can actually, from the energy which we are considering, we can deduce the value of this parameter epsilon. So let's see that. Let's try to figure out whether what I'm saying is correct or not. So we can rewrite, if I insert that one, I can rewrite the equation. So insert R min. And if we do that, what we get is the following. So let's just put these in parentheses. So this is going to be equal to gamma of mu divided by 2 of L squared. And then I get a gamma of 1 plus epsilon minus 2 times gamma. And I can reorder this one. And I simply get gamma squared of mu divided by 2 times L squared. And then I have 1 plus epsilon and epsilon minus 1, which clearly is something we can rewrite in terms of a new parameter, which I just call for B, this one, which is larger than 1, epsilon minus squared minus 1. And we know that mu is larger than 0. L is larger than 0, it's L squared. We know that this parameter gamma, we define that one to be larger than 0. And that means obviously that this term B must be larger than 0. So this means that if the energy is below 0, then it simply follows that this epsilon squared minus 1 has to be less than 0, which means that epsilon, which is a positive number, must be smaller than 1. So what we have is that 1, if epsilon is equal to 0, that gave us a circular motion. And if we then have epsilon slightly larger than 0 but less than 1, then we get elliptical motion. So we see now that we can link the value of this parameter epsilon, which we got from the solution of the differential equation, with the type of energy. And this is going to be a bounded motion because you will move either in a circle or in an ellipse. I mean, for the Earth, this epsilon is 0.08 something, so it's a pretty small number. So it's pretty close to 0. And that's reflected in the fact that the aphelion and the perihelion, R min and R max for the Earth, are pretty close to each other. If we go to Mars or Jupiter or any of the other planets, there's going to be a bigger difference between R min and R max. So let's now look at the other two cases which we can have. So what about putting this energy to 0? So we can put now E to 0. And in that case, we get a pretty simple equation to solve. We have epsilon squared minus 1 has to be equal to 0. And since epsilon can only be larger than or equal to 0, it's a positive number by definition, then epsilon is equal to plus 1. And then the question, what kind of motion are we getting here? So we can now go back to the solution of the differential equation. So which motion? So let's take a look at that. And the motion we are going to look at now with epsilon equal to 1, we're going back to the solution of the differential equation, and that is given by c divided by 1 plus epsilon times cosine phi. And since epsilon is equal to 1, this is simply c divided by 1 plus cosine phi. Now, already here, you see a problem. What can happen with the denominator here? If you look at that one, it can become 0. And you will see that reflected in the solutions, that you will actually see the object just disappearing. So you will never have a stable orbit here. So as these angles move from 0 to 2 pi, you will actually hit points where the radius goes to infinity. So this is already a signal that this is not going to be a stable orbit. So we can simply see that from the differential equation here and the solution to the differential equation. So this diverges when phi is equal to plus minus pi. So let's see now what kind of orbit we can get. So I'm multiplying the denominator, 1 plus cosine phi. So if we do that, we get r times 1 plus cosine phi, which is equal to this constant c. And then we remember that the r times cosine phi is the same as x. And then I just flip x to the other side. So I have c minus x. And then we square the equations. We know that r squared is equal to x squared plus y squared. In this case, actually doing this exercise leads to a very simple equation. So what I get then is x squared plus y squared, which is equal to c squared minus 2 times c times x plus x squared. And we see now that the x squared terms, they disappear. And if we now reorder it, we are going to get y equal to c squared minus 2 times c times x. And then I divide with 2 times c on both sides. So that means that I can get now an equation of x as a function of y, which is given by c. So I divide by 2 times c. So I get c divided by 2 minus y squared divided by 2c. And if we think of a famous equation here, we have an f of y, which in our case is going to be an x of y. And if we write it out as an a0 plus a coefficient a1 multiplied with y plus a coefficient a2 multiplied with y squared, we put now a1 equal to 0. a0 is equal to c divided by 2. And a2 is equal to minus 1 over 2c. So what kind of equation is this? What kind of shape does x take as a function of y? I see somebody, what's the name? A parabola. So we have a parabola here. So this is the type of motion we get when the energy is 0. So we have a parabola. So this is a parabolic motion. So let's go back to the figure which we had, and then we can bring back the type of motion which we're getting now. So we are now looking at this point here. So we have a point here where we are now E equal to 0. This corresponds to epsilon 1, and this is a parabola. So the next thing we are going to do now is to place ourselves here on the curve, and that means that energy is larger than 0. So let's go back, and then we take the last case here. So case 4. And now we are setting energy larger than 0. And you remember that the energy is given by, if we now assume that R dot at R equal to R min, so this is an assumption we are making now, is equal to 0. So we simply assume that the radial velocity is 0 at that point. If we now do that, then we have that the energy was given by this constant times epsilon minus 1. So what does this mean for epsilon? Now, let me just write it. So if you just think a little bit, let's just take 1 or 2 minutes. So which value should epsilon take? Can it be less than 1? 1 or larger than 1? So B is a positive constant. So which value does epsilon take here? Yeah, that's greater than 1. So when the energy is larger than 0, this is a case which leads to epsilon larger than 1. So in this case here, epsilon has to be larger than 1. And now we need to show finally that this leads to a hyperbolic motion. So the last thing we're going to do now is simply to manipulate the same equation for R in terms of the solution we have, and then see what type of motion we can get. So, and let's take a look at that. So we go back again to R of phi, which is our solution here. And that's given by C divided by 1 plus epsilon times cosine phi. And epsilon is now larger than 1. And we know that the denominator still vanishes. Denominator vanishes when we have a cosine phi is equal to minus 1 divided by epsilon. So that is also a case which simply tells us that we may have a radius which diverges. So if you simulate long enough, the object will actually escape. This is essentially what we are going to see when we also run the numerical calculations here. So we do the same exercise now. So we multiply with 1 plus epsilon cosine phi on both sides. And we introduce again that x is equal to r times cosine phi. So what we get then when we multiply out 1 plus epsilon cosine phi here, then we have r is equal, and then we move over epsilon times x. We have an epsilon multiplied with x here. And then we do the same trick. We square these equations. So then we square. We did the same when we did the elliptical and the parabolic orbits. So we get then r squared, which is x squared plus y squared. And that's equal to c squared plus epsilon squared times x squared minus 2 times c times epsilon times x. And then I take x over to the other side. So I get an x squared of 1 minus epsilon squared plus y squared minus 2 times c times epsilon x is equal to c squared. Now I can multiply with minus 1 on both sides because I just want this equation in a slightly different form. So I get epsilon squared minus 1, and we know that that's larger than 1. Then we get plus, no, this should be plus here, sorry, minus 2 times c epsilon x, and this is equal to minus c squared. And what I want to do now is to complete the squares for x. Complete square for x. So I need to introduce a new quantity. And the way I'm going to do that is to define a quantity which I'm going to call delta. So this is something which I'm going to define now, which is C divided by epsilon, divided with epsilon squared minus 1. And then I have a new parameter alpha, which is going to be given by C times this epsilon squared minus 1. And so this delta is simply epsilon times alpha here. And then I'm going to define an additional parameter, which I call for beta. And this is going to be C divided by square root of epsilon minus 1 here. So I can then rewrite this equation in terms of an x minus this delta squared. And this is going to give me x times epsilon squared minus 1. And then I have minus y minus this constant c squared plus epsilon squared of c squared, which is actually this delta. So I'm adding delta on both sides. And then I'm going to divide by epsilon squared minus 1 on both sides. And that gives me a new expression here, which is going to be simply given by x minus delta squared. And then I'm going to have an alpha squared here minus y squared divided by beta squared. And this is equal to 1. So this is the case where the energy is larger than 0 and epsilon is larger than 1. So if you now spool back to what you may have seen in mathematics courses, does this kind of expression remind you of a type of curve which you may have seen before? So with a parabola, we had a slight, or an ellipse, we had a plus there. So this is going to be not a closed curve, but it's going to be an open curve. Yeah, that is a hyperbola. So this is hyperbolic motion. And there is a nice figure in the textbook. If you take a look at that one, I'm going to bring it up here. So this is actually the hyperbolic motion which we get. There is an interesting observation which we can make here with that specific curve. If you now think of the physics of the motion which we may have, so this is the effective potential which we have. So this is our V effective. And we have placed ourselves at an R min here. So this is the closest which two objects can get. So this is an R here. In this specific case, what we assumed is that the kinetic energy and its contribution from the radial velocity is equal to 0. So that means that here we have only now a term which is given by, so the energy in this position here, so this is at R min. The energy is now given by L squared divided by 2 times mu of R squared min minus, and then we have the gravitational potential divided with R min. So one of the nice things now with the physical analysis, which we can make when we make this transformation to polar coordinates, is that now we can ask ourselves, which part of the energy is the dominating term here? So if you look at the curve and you have these two terms, which one is the one which dominates here? It follows from the mathematical expression as well. Say it again. The energy is larger than 0. So gamma is a positive constant. It's the term which goes like 1 over R squared. And this is the centrifugal barrier, which is set up by the kinetic energy. So when you have an angular momentum, which is different from zero, that means that the two objects can never get close to each other, because there will be a term which runs like L squared divided by 2 mu multiplied with the radius squared. And that's the one which kicks in at small distances. And that pushes the two objects apart from each other. So if we didn't have angular momentum, then the two objects could actually crash against each other. But due to the fact that we have angular momentum, that will actually push the two objects away from each other. So what you can do now, when you switch to polar coordinates, is this kind of physical analysis of the systems. Which are the driving parts of the physics, which you see here. So let's now bring back everything so that we have a nicer view on the type of motion which the gravitational force offers. And it's still useful to plot everything in terms of R here. So we have the energy here. So I'm just going to bring in everything like this. So this is our effective potential. So what we saw now is if we place ourselves here, that means that energy, the total energy is larger than 0. Epsilon is larger than 1. And then we have a hyperbolic motion. Then we have this position here. In that case, the energy is equal to 0. So that means that there is a total balance. And since we assume that the radial velocity is 0, there's a balance between the potential energy from the gravitational force and the centrifugal barrier from the kinetic energy. So they just balance each other. And on this energy scale, the energy is 0. And that means eccentricity equal to 1. So this is a parabola. And in both the hyperbola case and the parabola case, the objects are going to escape. So we will, due to the fact that the solution to the differential equation gives us a divergency, that means that the radius can actually go to infinity. So the objects will actually, after some time, they will be infinitely apart from each other. So this is roughly what happens if you think of a hyperbolic motion, when a comet is being deflected by one of the planets or the sun or whatever. Then we have, so these two cases, they give unstable orbits, so unbound orbits. That's a typical word which you will use in physics. So these are unbound orbits. So this applies to both cases. So both here and here. And then we are going to look at the other two cases. So we have the energy here. I'm going to mark like this. So this corresponds to an energy which is less than 0. So that means that it's actually the gravitational force which pulls in. And there is a balance between the gravitational force and the kinetic energy. And this balance stabilizes the orbits, which means that in this case, you will have bound orbits. And there is an R min, which we call an R min prime, and an R max here, prime. And this is a case when this eccentricity is less than 1, but larger than 0. So this is an ellipse. And finally, if we place ourselves at the bottom here, at this R min, then we have energy less than 0. We have this quantity epsilon equal to 0, and then we get a circle. And in that case, this is normally called bound orbits. I'm going to bring arrows here. So we have an arrow here pointing to that one, and an arrow pointing to the ellipse. So this in a way summarizes the type of motion which we will get when we have a gravitational force. Now, if you now think back to the previous homework, number 8, there we had a harmonic oscillator potential. Which kind of motion would you get in the harmonic oscillator? Elliptical, that's one, excellent. And then there's another type of motion you could get. Circular, perfect. So for the harmonic oscillator, you cannot escape. There is no way you can have unbound orbits in the harmonic oscillator. Then different types of potentials. If you now go back to what we had in the first midterm, you remember we had this potential which went like almost a harmonic oscillator, and then it had a linear term, which was meant to mimic the way quarks are confined. That's also a case where the objects cannot escape. So you would get elliptical and circular, but you would never get hyperbolic or parabolic orbits. So the object would never be able to escape from that specific potential. So this kind of motion is a kind of motion you can expect to see in essentially all types of physics cases, whether you do classical mechanics or quantum mechanics. And the powerful thing with the gravitational problem is that we have analytical solutions, and we can go back to the shape of the analytical solution and deduce all these types of motions and link that with the energy. So that's extremely powerful. And we are going to play around with these things in the midterm here. Okay, went a little bit over time. On Wednesday, I will sneak in a little bit more technicalities, but then we start looking at the midterm. And the same on Friday. Any questions? Feel free to ask questions and or hang around if you wish to. I'm going to stop the recording, actually.